Hello everyone, welcome to the course. Up till the last class, we were trying to understand what is the current market for hydrogen, where exactly are we using hydrogen and to what quantum. We try to understand that hydrogen as such has a very great market. We don't see it in our day-to-day lives, but in reality there is a huge number of applications where hydrogen is currently utilized. Now if hydrogen is getting utilized either in a pure form or a mixture, it also has to be produced from some forms. And we will be understanding this in the present and the future class, how hydrogen is produced even today. And we will be also understanding that majority of the hydrogen that we are using today happens to come from fossil fuels. It might be through coal or it might be through natural gas, but both of them are fossil fuels. And whenever we are using fossil fuels, the end result is that we would be emitting huge amount of CO2 into the atmosphere, and that is what the problem lies with the current production methodologies for hydrogen. So let us go further and try to understand how exactly are we producing hydrogen for the quantum of hydrogen that is required into our day-to-day lives. So as we have discussed that currently or the annual consumption of hydrogen is roughly 100 million tons or so, and majority of this hydrogen is sourced from either coal or gas. Of course, there is also some oil used in some places in the form of naphtha, but majorly it has been the coal or gas. So in the current class, we will be trying to focusing on how can I produce hydrogen from coal, or starting from coal, how do I get hydrogen as the major product. Further, I also need to say that because coal is primarily carbon, more than almost 90% of the composition of coal is coming from carbon, and inevitably this carbon would be released to the atmosphere and most of it goes out as carbon dioxide, which is why we say that the current production of hydrogen is very carbon intensive, and the hydrogen that is produced from coal or similar sources is termed under the name or the nomenclature of grey hydrogen, because we tend to release significant amount of CO2 when we are producing hydrogen from coal. Now if I take any generic coal, normally it would have 60 to 80% of carbon by mass, depending upon where the coal is getting sourced from, and of course coal will also going to have different kinds of impurities. If I talk about the hydrogen percentage in the coal itself, it's roughly of the order of 5%. So not very great amount of hydrogen is there that is a part of the structure of the coal. So how do I really get hydrogen out of coal? Well, of course, we try to extract some of this hydrogen that is inherent in the coal, but we also use a phenomena called gasification, wherein we are trying to react coal or heat up coal in an insufficient supply of air through a process called gasification, where we are producing a gas that is rich in hydrogen and carbon monoxide. Now this gasification might also be known through other names like partial oxidation. It's basically a reduction occurring at high temperatures and in insufficient supply of air. So let us try to get some understanding of what really we mean by gasification process. So when I say gasification, it's basically a closed chamber in which we are heating in coal in an insufficient supply of air. So what happens in this chamber? A lot of reactions happen. So let me note down some of these reactions for you. The first or the very first reaction that would be occurring would be combustion. By combustion I mean the carbon reacting with oxygen producing CO2. Then another reaction that occurs is the steam carbon reaction. So this is the carbon reacting with steam or the inherent moisture in the coal to produce carbon monoxide and hydrogen. So if you note down what is the source of hydrogen in here, it's basically coming from the water molecules. Then there could be something called as hydrogasification, wherein the carbon which is present in coal would react with hydrogen that is produced and might produce methane molecule. Further, there is also an interesting reaction which is called the Baudard reaction, and this happens to be the carbon reacting with the carbon dioxide that is produced to produce molecules of carbon monoxide. Then these are a few solid and gas phase reactions which are heterogeneous in nature. There will be also a few homogeneous reactions like water gas shift. So what happens in water gas shift? Carbon monoxide which has been produced reacts with water and tends to produce hydrogen and CO2. So you see more hydrogen is coming from water in here, and then there is another gas phase reaction which is called methanation, wherein we would have the carbon monoxide reacting with 3 molecules of hydrogen producing in methane and water. So majority of these reactions are reversible reactions, so they go in both ways depending upon the temperature and the pressure conditions that are prevalent, but these are some of the major reactions that would be occurring in the gasification process. So remember that herein we are providing oxygen that is less than what would be required for combustion. So it is not combustion that is happening here, but a partial oxidation wherein the amount of oxygen that is required would be way less than that would be required for the complete combustion of coal. The result is that the reactor or the gasifier operates at roughly 800 to 900 degrees Celsius, and the resulting gas would be rich in hydrogen and carbon monoxide. We also need to understand the concept of equivalence ratio in here. So if I say the equivalence ratio, this is defined as the weight of oxidant and divided by the weight of dry fuel, which happens to be coal in our case, and the oxidant happens to be oxygen, and this divided by the stoichiometric weight of oxidant, which is the amount of oxygen that I would require for the complete combustion of coal, divided again by the weight of dry fuel. So basically what I am doing is I am trying to estimate or trying to get how much amount of oxygen I am putting in with respect to the amount of oxygen that would be required for the complete combustion of coal. And this number happens to be roughly of the order of 30 to 40% in the case of gasification. So if this equivalence ratio, I might mention this with the name ER, if this ER happens to be greater than or equal to 1, what I am aiming for is combustion. So what we see in the normal boilers is that we are combusting coal, where we are providing exactly or more than the amount of oxygen that would be required for complete combustion of coal. If this ER happens to be less than 1, roughly of the order of 0.3, this is what I called gasification. And if this ER happens to be equal to 0, the process is called pyrolysis. So when I say pyrolysis, I am just heating up the coal in an inert atmosphere. There is no oxygen that is available, and the result of pyrolysis, depending upon the heating rate and the temperature, would be either we are getting a lot of char that is getting formed after the escape of volatiles, or what we are producing is something called as oil, which could be a substitute for different grades of oil that are produced. But pyrolysis is not something that we are aiming for. We are aiming for gasification. We are providing an oxidant, but this is less than what would be required for complete combustion of coal. We can also try to understand this with the help of a simple video, which again I am trying to show a few snapshots about. Again, the YouTube link is given to you. So this video is by NETL. So let us try to get a glimpse of how does gasification happen. So this is true for any element like coal or even biomass, which is composed of carbon, hydrogen and oxygen. And this is what you see in here. So we are looking towards woody substance or a coal-like substance that would have carbon, hydrogen, and if I talk about the complete combustion, it normally leads to the production of CO2 and H2O. This is when the complete combustion is happening with the ER greater than 1. This is what a gasifier looks like, and normally you would have the coal entering along with some oxygen, and there might be some steam also entering, and this oxygen is going to react with carbon to produce carbon monoxide. The hydrogen in the water molecule and the hydrogen from the coal escapes at H2 gas, and the water can also react with carbon to produce more H2 and CO. So ultimately the result is a gas that is rich in hydrogen and carbon monoxide. So this is what we are getting at the output, and this is what I called syn gas or synthesis gas, a gas that is rich in carbon monoxide and hydrogen. And this is not a new technology. This phenomena has been known to us for quite some time, and this was one of the earliest ways of production of some of the hydrogen derivatives like ammonia, where the process like this was used to produce syngas, and that was later on conditioned. Now there is, after this, once you have a gas that is rich in carbon monoxide and carbon dioxide, you could enhance this reaction by converting the remaining carbon monoxide into more hydrogen, cleanse the gas, and at the end you can produce pure hydrogen. We will be discussing this in more detail as we go further, but the phenomena is going to be the same even if we are going towards a feedstock like biomass, which again will be a matter of discussion in the future classes. Now, one important thing that we need to keep in mind while going through the gasification process is that there is a lot of uncertainties involved based upon the feedstock, based upon the composition of the coal, based upon the oxygen that we are using. Either we are using only oxygen, or we are using air, or we are using some amount of steam. There might be different reactions occurring. There might be a difference in the temperature that the gasifier is operating at, the residence time, and all this tends to dictate the composition of the gas and the efficiency of the gasification process. Sometimes we might want to work at a higher temperature. Suppose if I increase the oxygen, I might be operating the gasifier at a higher temperature, but at a higher temperature we might want to lose some of the precious products, which might bring down the amount of synthesis gas that we are able to produce. So there is a trade-off in this process, and process optimization is a key thing when we are aiming for a process like gasification. Now there could be different kinds of gasifiers, or there are different kinds of gasifiers that are available in practice, but majorly they can be divided into three major categories: moving bed, fluidized bed, and entrained flow gasifiers. So let us try to understand what these three types of gasifiers are. So when I say about the moving bed gasifier, these are one of the oldest types of gasifiers that have been used. One of the major model that was used historically was the Roorkee gasifier, and it was initially developed for black coal, and the aim was to produce synthesis gas for the production of ammonia. So I am talking about almost 100 years back, when there was a need for ammonia both for explosives and fertilizer production, and there were gasifiers like this developed for in places where coal was available in plenty. But the problem with this particular gasifier was that this was operating at a lower pressure. So there was some kind of modifications done by British Gas, and the modified version came to be known as the British Gas or the Roorkee gasifier, which could be working at advanced conditions, which basically entail higher pressures and could be working with different oxidants like oxygen and steam. Further, we need to understand that normally the capacities of these gasifiers are small in nature. So normally if you would have a plant that is working at a larger capacity, there would be many gasifiers that would be used in series. Normally the operating range is of the order of 30 bars or so. And there are many gasifiers that are currently in operation with the feedstocks such as coal, leading to production of synthesis gas, which could be used for different industrial applications. If I talk about the operation of this type of gasifier, so normally you would have the coal getting fed from the top. So this is, and the gasifier is basically like a closed vessel. So you see the closed vessel in here, an insulated closed vessel, wherein the coal would be fed from the top, and the coal could be coming in the form of lumps. So further there would be a feed locker, because we would need to make sure that the oxidant is almost of the range of 30%, or maintaining equivalence ratio of 30%. So the coal falls on a grate which happens to be rotating, and there basically it forms a bed which keeps on moving slowly as the grate rotates. So the grate is basically rotating at a certain frequency so as to make the ash and any of the char that is produced fall in the bottom pit. The gas that is produced might have certain impurities, because as soon as the coal falls on the hot bed, there is a process called pyrolysis, as we discussed, also happening, and this pyrolysis leads to production of tars or heavy oils, and these heavy oils tend to contaminate the gas. So what you get here is a crude gas which need to be cleansed with the help of methanol wash or some other kind of purification technologies. And again you have this grate which would be rotating, and because of the rotation of the grate, the bed will be slowly moving, and this is why it is called a moving bed gasifier. The normal temperature is of the range of 800 to 900 degrees Celsius, and then you also tend to have an inlet for steam and oxygen. as such, this is a compact gasifier, has been used a lot in historically, but the size is a limitation. And further, another limitation with this kind of gasifier is that the gas that is coming out is not very pure. So again, that tends to have significant amount of tars or heavy molecular weight compounds which needs to be removed, and that is one of the limitation of these kind of gasifier. So if you would want to have a look at what this kind of gasifier looks like, this is basically a picture for visualization. So this is one of the gasifier that is being taken to a site. Then another kind of gasifier that is used at a larger scale or available at larger scale is the fluidized bed gasifier. So as the name suggests that it is basically operating in the fluidized regime. So just to explain to you people who are not aware of this fluidization phenomena, it's basically the coal is entering in the form of very small particles, and then this is subjected to a very huge velocity of the oxidant. So imagine that this is formed from the coal and some kind of bed material which could be sand or silica in nature, which does not react with coal, and then there is an oxidant which could be oxygen or steam coming from the bottom of the gasifier, and this would be coming at a very great speed, and the speed would be such that this bed is going to act almost like a fluid. So this is what I called a fluidized bed regime or a fluidized bed gasifier, that the solid particles of coal and the bed material are made to act like a fluid. So what is the advantage of this kind of gasifier? The advantage mainly lies because of the heat distribution. So in the earlier case of the moving bed, there is an uneven heat distribution. There could be some kind of heat zones or that might be created that might not be good for the gasification process. Some parts of the reactor become much hotter than the other, which lead to uneven operation and uneven production of the gases. Whereas in this case, the temperatures could be very evenly distributed, but this also comes at the expense that we would have to grind the coal to the finer particles. Further, the operation wise, it's like it also has a bit of challenges in the sense that now the oxidizing medium has to play two roles. It has to provide enough oxidant to meet the equivalence ratio, and plus it also needs to be coming at a velocity such that the bed is in a fluidization regime. So control of this kind of gasifier is somewhat of a challenge, but if you talk about the larger scales, this kind of gasifiers have found to be economical and are also better performance such that the syngas or the synthesis gas that I am getting is of a better quality with much less tars coming in. But there is also an issue in here, because normally what is going to happen is that you are going to have the coal coming from here, from the lock hoppers, and the different kinds of oxidants coming in here. There is going to be some kind of char production, and this char might enter the synthesis gas. So this could be because ultimately you would have the gas cleaning to happen. So normally downstream you would have some kind of cyclone wherein the gas is going to get purified, but there could be some types of impurities in the form of char entering into the gas and might be contaminating the gas. If you talk about historically, like this was developed by, this was known as the Winkler gasifier, or the later on taken over by a company called KBR. And if you would want to look at some of the examples like UGas type 5 gasifiers, is a typical example of this kind of gasifiers. Again, these kind of gasifiers might operate in two regimes, which could be the bubbling fluidized bed and the circulating fluidized bed. So in the bubbling fluidized bed, what is happening is that the bed height is sort of limited by the air velocity. So the bed only expands to a certain limit, and this is what is called a bubbling fluidized bed, so that the velocities of the incoming oxidant are near the minimum fluidization velocity. Then the other regime that normally is used is called the circulating fluidized bed, wherein the fluidization velocities are way higher, such that the whole bed exists and then comes back through the cyclone, and this is what is called the circulating fluidized bed. Both the technologies have their own pros and cons. We wouldn't go into the detail, but these are the two main variants that are available in fluidized bed. Then continuing with the types of gasifier, the third type of gasifier that is available, that is used on large scales, is called the entrained flow gasifier. Again, and this is also a pretty old technology, is developed in the 1950s, and earlier this used to be known as the Koppers-Todzek gasifier, and this is basically the basis for the Shell gasifier or the Ude pen flow gasifier. So what happens here is the coal is taken in a very fine powder, and it's basically introduced in the bottom part of the gasifier. And one of the things that is a phenomenon of this gasifier is the high temperature that is reached. So normally you would be working at a temperature of roughly 1400 degrees or so, Now the advantage of working at such a high temperature is that the ash is going to melt and is going to slag along the walls of the gasifier and fall down. So the operation is somewhat of a difference as compared to the moving bed gasifiers in terms of the temperatures are very high. You would not get any contamination or very less contamination in the form of tars, because at such high temperatures most of the tars are going to crack up. So the major advantage of this kind of gasifier would be that the gas that you are getting is very pure, so that the downstream cleansing is not required much. Again, there is a trade-off here. So in the case of moving bed gasifiers, you would need no pre-treatment terms of coal, like coal can be entering as lump, but the gas that is created is not very pure. Whereas in case of the entrained flow gasifiers, I would need to have very fine particulate coal, so that needs a pre-treatment in the form of coal, but the gas that I am getting is very pure, so that the downstream gas cleansing is easier. Again, just to show you the operation, so this is what the shell gasifier looks like. So this is the shell gasifier, wherein you would have, of course, it has biomass written in here, but this is equally applicable to coal as well. So you would have the coal entering in here, and then you would have the different kinds of gasifying agents entering, and because of the huge flames that are coming in, the ash is first going to rise up in the form of slag and then melt down and the form of residue material, and the cleansed syngas, because of the high temperature, is basically coming out from the top. Another variant of this particular gasifier is also called the Texaco gasifier, and this is what you see on the figure on the left. So the operation is somewhat slightly different in the form that you would have the coal or biomass entering from the top along with the gasifying agent, and what happens here, the coal is entering in the form of slurry. So it's mixed with steam and it enters almost like a slurry, and because this slurry, the gasification is quite fast and the temperature reached is again very high, and further the gas is escaping from the bottom, and what you get in the bottom pit would be the residual ash or the char that is coming in. Again, both of the gasifiers have been used successfully in the past. Now let us also try to understand what kind of gas that you will be getting from these kind of gasifiers if the same coal was used in different gasifiers. So with respect to the operation of the Shell and Texaco gasifier, but again we need to understand that, like, the main contaminant here is the ash that would be getting in, and that is easier to bring in. If I talk about the pre-treatment, you need the cost of a pre-treatment of coal that is coming in, and further the gas conditioning is not much required. So this is what an entrained flow gasifier looks like. Now let us also try to have a look at the comparison of different kinds of gasifiers if they are using the same amount of coal. So this was data is coming from the source that is given at the bottom of the slide. So the same kind of coal was used in different gasifiers, which is the moving bed gasifiers in terms of the Roorkee gasifier and the British gas Roorkee gasifier. KRW is basically the fluidized based gasifier. So this is the Wrinkler gasifier that was taken over by the company called KBR. And then we have these two, Texaco and the Shell gasifier, representing the entrained flow gasifier. So if I look at the pressure conditions, the original Roorkee gasifiers can work at atmospheric, so that is a limitation, whereas the other gasifiers are known to work at elevated pressures, roughly almost of the order of 30 bars. Now if I look at the composition of the gas that I am getting, it could be somewhat of difference. So if I look at the Roorkee gasifier, it's going to produce almost 50% of hydrogen in the gas, so that is quite good, and then another 30% in the form of carbon monoxide. The carbon dioxide and methane happens to be around 10%. Now this is somewhat different from other gasifiers in terms of the British gas, fluidized bed and the entrained flow gasifier, where the majority of the gas was going to be form of carbon monoxide, and then hydrogen is going to be on a lesser side. Now this is not a cause of a worry, because downstream of these gasifiers normally we would going to have a water gas shift reactor. So what happens in a water gas shift reactor is the carbon monoxide is made to react with water and produce hydrogen and carbon dioxide. So if a gasifier is producing more carbon monoxide than hydrogen, it's not a case of worry. Of course you would need an extra equipment downstream, but majority of this carbon dioxide or carbon monoxide is eventually going to get converted into hydrogen. So carbon monoxide is equivalent to hydrogen in this case. So what we need to be concerned is to see the total amount of carbon monoxide and hydrogen that is produced in the output gas. Further, we are also going to have other hydrocarbons which are going to be on a higher end in case of the moving bed gasifiers because of the low temperature conditions. and these gasifiers or the sulfur in the coal would normally get converted into H2S gas, which could be different based on the reacting conditions. And also in some of these gasifiers the H2S or the sulfur is going to form carbonyl sulfide, which can be some of a problem. Further, we also need to see the total amount of hydrogen and carbon monoxide that is produced, that is important to us, and you see that the entrained flow gasifiers seem to be leading in that. And if we see this gas composition on a dry gas basis, which is even after removing the moisture, we would notice that like entrained flow gasifiers tend to have the best output in terms of the gas that is produced, would have the highest amount of hydrogen and carbon monoxide. Of course, as I have reiterated and will be discussing in the future classes as well, the carbon dioxide being produced in a greater amount is not much of an issue, because ultimately downstream we are going to have some kind of water gas shift reactor where the carbon monoxide is getting converted into hydrogen, and then finally we would have to remove the CO2 to produce pure hydrogen. So these are some of the major kinds of industrial gasifiers that we have in operation. Further, there is another interesting phenomena that is now being explored for the production of synthesis gas from the coal that is unminable. Now there are many coal mines where like extracting coal from the depths of from the mines might not make economic sense. So people have come out with the idea of underground coal gasification. So what happens in underground coal gasifications is that instead of extracting or mining coal out and then gasifying it, why don't we supply some kind of oxidizing agent in the form of oxygen and steam to the coal seam and make the coal gasify in the coal seam itself. The resulting product gas can then be extracted and can then be used for different purposes, which could be either for production of different grades of chemicals or the production of electricity. Further, the CO2 that would be a part of this gas could be captured and later on sequestered as well. So this could be an additional option. So just to give you a visualization of how this kind of process would work. So first we would have to go to a coal seam. So you would see that normally you would dig in some kind of a pipe with a depth of more than 300 meters and going up to a couple of kilometers. So this is a drill that has to be more than 300 meters or so, and so this is basically drill. And then at the other end of the coal seam you are going to make another drill, which you will just see in this with the help of this video. So then there is another drill that is made in the coal seam, and the aim here is basically to pump in the different kinds of oxidants in the form of oxygen and steam. So once you have these two drills getting connected, you would basically have the supply of oxygen that would be starting. And of course, most of these setups are modular in nature, so that you have the operation could be much easier, so that they could be shifted, and once the coal seam is utilized you can go to other places and extract a similar way. So now then there is an ignition tool that is basically started, which is basically to start the ignition process, so that there is going to be some kind of combustion that is initiated, and then the gasification process can go on. So here you would have some kind of ignition mechanism that goes on into the coal seam, creating the ignition, and this basically initiates the gasification process. So you would have the gasification occurring in the coal seam itself, and the result would be a gas rich again in hydrogen and carbon monoxide, wherein you also see that oxygen is added, and this is what is going to sustain the gasification process. So the gasification is occurring within the surface, and then the synthesis gas is coming out, which might be captured and used for different applications. So this could be a way in which where you are using the coal that is unminable and carrying out the gasification in the mines itself. So with this we have tried to understand the major pathways for production of or major like equipments in the form of gasification, or the gasification pathways for the production of hydrogen from coal in the current class. In the next class we will try to understand what could be the pathways of production of hydrogen from natural gas. With this we end the current class. Thank you.